everybody. The topic today for my talk is recent developments of the mixed Andre-Oort conjecture. So first of all, I want to review something about this conjecture, this statement. Let's quickly review the theory of modular curve y1 here. Associated to an elliptic curve, there is an invariant called the J invariant, and it satisfies the property that two elliptic curves are isomorphic to each other if and only if their J invariants are the same. Second, let's take H plus the upper half plane. Then for any point tau in H plus, we can define the quotient of C by this lattice Z plus tau Z. And then this E tau is an elliptic curve. Furthermore, there is a group action of SL2R on this upper half plane by this formula. And third point is we can define another map, which we also call J, from H plus to C, sending every point tau in H plus to the J invariant of the elliptic curve E tau. Then this new map J is a complex analytic, and J tau equals J tau prime if and only if tau and tau prime lie in the same SL2Z orbit. So, therefore, this map J induces a bijection from H plus quotient out by SL2Z to C. The discussion above realizes C as the modular space of elliptic curves, which we usually denote by y1. It has a uniformization H plus to y1 defined by the J in the third point here. Okay. For any positive integer larger or equal to 3, we have a similar object yn, which first of all is also an algebraic variety of dimension 1. And secondly, the points on yn parameterize the isomorphic classes of elliptic curves with level n structure. And there is also the uniformization H plus to yn defined similarly. Here I want to talk about level structure because when n is larger enough, here n is larger or equal to 3, then this yn is a fine modular space so that we have a universal family over it. I call this universal family En. It means that we have a projection from En to Yn such that over each point small y in Yn, the fiber of pi is isomorphic to the elliptic curve represented or parameterized by y. Now let's take a closer look at En. We want to study the uniformization of En in this case. It has a natural uniformization. There's a natural candidate R2 plus R2 times H plus, and we want to put some complex structure on this R2 times H plus. For H plus, there is no problem. H plus is embedded into C very naturally, but for the complex structure on R2, we have two different points of views. First, we can fix an identification from R2 times H plus to C times H plus. And then we let the lattices Z2 in C vary from fiber to fiber to get a universal family. Second, we can also fix a lattice Z2 into R2. And then we let the complex structure of R2 vary fiber by fiber to get a family. And here it varies in the way that over tau inside H plus, we identify R2 to C by sending AB to A plus B tau. In my talk, I will take the second point of view. The first advantage of this point of view is that then the universal elliptic curve can be written as a quotient of R2 times H plus by some group here. Okay. Now the Andre-Oort conjecture for this universal elliptic curve is the follows. First, we define special points on this universal elliptic curve. They are precisely the points parameterizing torsion points on CM elliptic curves. The conjecture is the follows. Let Z be an irreducible proper subvariety of En. Then, because En is of dimension 2, Z must be of dimension 0 or 1. We suppose that Z contains a Zariski dense subset of special points. Then Z is either in dimensional 0 case, it's a special point, or it's in the dimensional 1 case. There are two subcases. Either it's vertical, then it's just a fiber of the projection, or it's horizontal, in which case this is the only non-trivial statement for this case. It says that in horizontal case, it must be an irreducible component of a subgroup scheme. And this conjecture was proposed by Yves Andrè in 1993 in a talk. And in this case, this conjecture was proved at the same time using a height inequality of Silverman. Okay, so this is the dimensional 1 case, elliptic curve. And for higher dimensional case, there is also a parallel theory for a universal abelian scheme. So for any positive integer n, there is an algebraic variety we call AGN, such that this algebraic variety is the modulus space of principally polarized abelian varieties with level n structure of dimension G. Moreover, there is a uniformization from the Ziyang Gao upper half space to AGN for any n. Also, when n is large enough, here n is larger or equal to 3, this modulus space is fine. So there is a universal abelian scheme. I call this curly AGN over AGN. There's a universal abelian scheme. And this universal abelian scheme also admits a uniformization similar to the elliptic curve case. So here it's R2G times HG plus, which I will denote by x2G plus for simplicity in my talk. And we also take the second point of view, it as we fix a lattice in this R2G, and we let the complex structure on R2G vary fiber by fiber to get a family. And then we can write this universal abelian scheme as a quotient. The Andrè-Oort conjecture for this case is the follows. First, special points are defined similarly. A point is special if and only if it represents a torsion point on a CM abelian variety. I denote by pi the projection from the universal abelian scheme to the modulus space. The conjecture is the follows. Let Z be an irreducible subvariety of the universal abelian variety. If Z contains a Zariski dense subset of special points, then Z is a special subvariety. Special subvarieties I will give another definition in the next page, but here I want to say in this case, in this particular case, there is very good modular interpretation. So it means that pi Z is a totally geodesic variety with a special point. I didn't write here because with a special point is given for free. So for the base, we ask it to be a totally geodesic variety. And on the fiber, Z must be an irreducible component of a subgroup scheme. So the statement is really similar to the dimensional 1 case. This conjecture was proved, I think, 3 months ago. After a series of work. So you can either use Pilat-Zimmermann or Klingler-Ulomi-If, and the lower bound proved by Zimmermann 3 months ago, and my contribution is to generalize everything for a pure Shimura variety case to mixed Shimura variety case. This is the general form of this conjecture, and it's also a more economic way to state it. Let's take S a connected mixed Shimura variety and Z an irreducible subvariety. If Z contains a Zariski dense subset of special points, then Z is a mixed Shimura variety. Before proceeding, I want to give some examples of mixed Shimura varieties which are not pure. The first example is what we talk about, the universal abelian variety. And the prototype will be this one, the universal Poincare by extension over the moduli space. Okay. Next, I want to... So, this is the modular space. On this modular space, you have the universal family, and you can take the dual of this universal family, and on it, you have a GM tosser, which is the line bundle on each fiber is the Poincaré line, Poincaré by extension of that. And this is because actually every point on a modular space is already has a polarization. So this thing is not good enough because it doesn't parameterize. It doesn't tell us what the polarization is. So there must be something over this one for the prototype, and this is the case. Okay. Now I want to give an outline of the proof using a Pilat-Zanier method. So some notation is I will denote by sigma the set of special points of the mixed Shimura variety S. First step is to prove a so-called Ax-Linderman theorem. Okay. The theorem, I will stress it here. So first of all, I want to say that Pink defined a class of subvarieties which are called weakly special for any mixed Shimura variety. I don't want to repeat the exact definition here, but but we can see in the example of the universal abelian variety what they are. They have also modular interpretation in this case. So let Y be a subvariety of the universal family, and we take pi inverse pi Y to pi Y. This is an abelian scheme, which may have an isotrivial part, and we call this isotrivial part C. So in this case, the modular interpretation is the follows. This Y is weakly special if and only if two things are satisfied. First, in the base, it is a totally geodesic subvariety. This part is proved by Ben-Monen. And the second part says something about in the fiber how it behaves. So then this Y is the translate of an irreducible component of a subgroup scheme. This is this is the one for the special one. But here we also allow a translation by a constant section for the isotrivial part. So this is the weakly special thing in this special case. The theorem of Ax-Linderman is the follows. Let's take X as a mixed Shimura variety and the uniformization X plus to S. This uniformization, for example, in the universal abelian variety case, it's the X to G plus. A priori, this uniformization is highly transcendental. So it's highly transcendental. Now let's take Z tilde, a connected semi-algebraic subset inside X plus. And we want to study the image of Z tilde under this uniformization. Since this uniformization is transcendental, the image is a priori, it could be as bad as possible. So first step to study the image is to take the closure of it. And here we take the Zariski closure. And then the theorem says that every irreducible component of this Zariski closure must be weakly special. This theorem, the first very important case of the theorem is proved by Pilat in 2011. This is the breakthrough point of the Andre-Oort conjecture. And also, the theorem talks about mixed Shimura varieties, but before that, there is a theorem about pure Shimura varieties proved by Klinger, Ulmo, and FIF. Although this is the most general form, in my proof for a mixed case, I still use a counting result of Klinger, Ulmo, FIF, not really the full theorem. Okay. So that's the first step. The second step is deduced from Ax-Linderman a result about distribution. This is not very hard and have been done by several people separately. The third step is to choose a good fundamental domain for the uniformization. So there are natural candidates for this for fundamental domain. The thing here is to prove that this is good. It means that it behaves well under some old minimal structure. And this is also proved. And we associate to each special point a parameter called complexity. First step is the upper bound. And this is proved by Peter Timmerman for the modular space case, and Andrè-Oort for general Shimura variety, including exceptional type. Fifth step is the very new result, the lower bound of the size of Galois orbit of special points with respect to their complexity. So this is the result which was proved in 3 months ago. So first of all, I reduced this lower bound for mixed Shimura varieties to the pure part. Then for the universal abelian variety case, or even more generally for Shimura varieties of abelian type, it suffices to prove the following conjecture of Edix-Cowen. Now we take any special point in the modular space, and we denote by AX the CM abelian variety parametrized by this point. Let Rx be the center of the endomorphism ring. Then the Galois orbit, the size of the Galois orbit of X is uniformly bounded below by the discriminant of the center of the endomorphism ring. Okay. And this conjecture has recently been proved by Timmerman. Here I want to address the main idea of his proof. So the starting point of the proof of Timmerman is this theorem, Maser-Wistholz. Let AB be abelian varieties over a number field which are isogenous over the K-bar. Then there exists a constant CG such that the minimum degree of isogenies from A to B is bounded from above by the maximum of the Felting's height of A and the degree of K. Okay. So let's take a closer look at this theorem. First of all, the term K over Q, this is essentially the Galois orbit of X, well, up to a constant otherwise. Then when A is Cm, the left-hand side is easy to control. We can produce a B isogenous to A with the minimum degree of isogeny large enough. And therefore, to prove the desired lower bound, it suffices to bound the Felting's height of A from above. And then the Coulomb-X conjecture comes into the picture. The Coulomb-X conjecture expresses and a CM abelian variety, its Felting's height, in an explicit formula whose terms can be bounded by classical results. And therefore, it suffices to prove the Coulomb-X conjecture, which is perhaps harder, even harder than the conjecture before. But since this Felting's height is bounded below by a constant depending only on the dimension of A, it is enough to prove an average version. Here, average means that we sum up over all the CM types. This average version is known by recent work of Xunyi Yuan and Shou Zhang, or separately by Andre-Oort, Goring, Howard, and Matapus-Pera. So to summarize, this lower bound is also known. And sixth step, it requires some work, but in this Andrè-Oort conjecture case, it's very simple. So I just put one word here, it's conclude. And in summary, here is the theorem. The Andrè-Oort conjecture holds for any mixed Shimura variety of abelian type. And for exceptional type, I think it's far from being proved at the moment. Okay, thanks for listening.